Things that we talked about a little bit last time is a lot of online tools will use a convention for which base you mean when you just type log of x. Let's figure out which convention Desmos means by thinking about what logarithms mean. So let's pull it up. There's Desmos. There's log of x. Let's see, log base b of x. This is like the inverse to y equals b to the x, right? That's the whole point of logs. They undo exponentials. So that means that the graph of log base b of x should be the same as b to the x, but with x and y flipped. Fair enough. So let's try to do exactly that. Let's sketch the graph of x equals b raised to the y. I haven't said what b is yet, but let's just add a slider. We want to figure out what base these work out to be. So, in purple now, I guess that purple thing should be the inverse function to 2 to the y, so that's log base 2 of y. So what do you think, according to this, when you type log of x in Desmos, does it mean base 2? No. I don't know. What are some guesses what it might want? Yeah.
10.
Let's try 10. Look like it lines up pretty well? Yeah. Maybe one other we'll see. There's the so-called natural logarithm. What base did we say that was? Base E for Euler's number. And there, you see it lines up pretty well. Folks feel pretty okay about this idea of a demo? Nice. So let's use logs for one of the reasons that they were invented. They're invented to study exponentials. Let's use them to study some exponentials. Let's solve some equations. Here's one that you might remember from last time. 5 to the x equals 7. Let's try to solve that. What seems like a good strategy? Don't share a base, so we can't use the strategy where we try to rewrite everything with a common base. Does that look like an equation in exponential form?
Yeah. Should we use a logarithmic function?
Let's use a logarithm. Let's rewrite that in logarithmic form. So, what do you get when you rewrite that in logarithmic form? I guess what's the base? The base stays the same. So yeah, let's put this on the board. No, let's put it on paper so it's in the recording. B to the x equals y. Here we see an equation in exponential form. You can color code it a little bit. So if you take that thing in exponential form and put it into log form, you get the new equation, log base b. So the base stays the same, but now it's the base of a log instead of an exponential, of the thing on the other side, I guess let's use parentheses, equals x. So if you rewrite this in log form, the base is still 5. So now it's log base 5. What's inside of those parentheses? 7. And that should just be equal to x. Hey, cool. Have we just solved for x? Nice. If we wanted a decimal approximation, let's get a decimal approximation. And in order to demo one fact, which I won't justify today, but will want to use occasionally, happily the lid was closed. Let's try to ask Google, what's the log base 5 of 7? So there's like a standard way to type it. But you notice Google doesn't know what to do with that. If you look at your calculator, how many people know how to use their calculator to walk in different bases than it uses right now? Cool. How do you do it? There's a button.
I suppose just like the example of log base 5, 7. I type in log 7 and then divide that by log 5.
Awesome. So here's a fact that we won't justify today, but we will justify in a few days. If you can walk with respect to one base, you can walk with respect to any base. Oops, couldn't see that. If you want to compute log base 5 of 7, just divide by the log of the thing in the base. Log 7, divide by log 5. About 1.2. That feel pretty okay? Nice. So let's try to solve some more complicated equations. Here's another one. 3 to the x, then squared, is equal to 8. And there are two different strategies to follow. So maybe here's what I'll do. I'll give you some time to think on this. We'll come together and see what answers people settle on. If you like, get exact answers and a decimal approximation if possible, and we'll compare them. Yeah.
I just want a question, just a little bit curious about this. Am I supposed to log these X to the appearance with the X and Y flip? Do the same thing? On the chart.
No, sorry. So, which...
Because on the board you have like Y equals log BX, and up here you have log BY. No,
Oh, cool. So, read the whole sentence. So, the log base b of x equals y is the inverse to y equals b to the x. So the word inverse isn't up there. Let's unpackage what the word inverse means. So what this means is log base b of x equals y means exactly this equation, but where x and y are flipped. Which hopefully now it's correct. Because that's what inverses do. Good question. Thank you. All right. So, the next thing I want to do is I want to, while you think on this problem, I'm going to hand back some exams that are graded and now in Canvas. So I'll do that. Okay. Anyone have an answer they're confident in? What'd you get?
I got about 0.95.
X about 0.95. How confident are you?
Moderate.
All right. So I'm going to propose doing the following to check. Do you think we could graph both sides of this equation? See if that decimal looks reasonable? I think we could. I guess maybe I should ask this before we do that. Did anyone get different decimal approximations? All right. Anyone get the same? Cool. I guess that's some confidence then. So let's graph both sides of this. Let's graph 3 raised to the x, parentheses matter, and then you square that. And let's also graph y equals 8. The solution is the point of where they cross. Does that look about right? I believe the decimal approximation, but what do you think? So let's also talk through where that solution came from. So what was your first move?
I basically just solved for x, so I did a log base 3 of 8, and then divided it by 2.
Log base 3 of 8, and then divided by 2. Neato. So there's like a 4-step that you did, which I'm going to write down.
Right. Set it as a log.
Well, before even that, that's something you did, right? Oh, god damn it.
Square the 3x.
Yeah, which would put the 2 inside of the exponent because we have exponential laws. Next, as you said, you're going to rewrite this in log form, or take the log of both sides. 2x equals log base 3 of 8. And then what did you do last? Divide by 2. Cool. Any folks follow a different strategy? Well, there is another one. But there's always multiple ways to solve a problem. In particular, this equation, there's only one x in it. So one way that you can try to solve an equation where there's only one instance of the variable is take every move you see on the side that has x's and try to undo them in the opposite order. So here's another strategy. This is, I think, the better strategy, but I want to show the other one because it might reveal something interesting. The way to read the left-hand side is you take x, you put it in the exponent of the 3, and then you square it. So let's undo those one at a time. What undoes squaring?
Square root.
Square root. So here's another possible first step. 3 to the x is equal to plus or minus the square root of 8. And let's think about that plus or minus. Can 3 to the x ever be negative? No, exponentials are only ever positive. So do I actually care about that negative sign?
No.
Right. So in this case, the plus or minus subtlety goes away. All right. How would you solve that for x? Does that look like an equation in exponential form? Let's put it in log form. So whenever you see an equation in exponential form and the variable is in the exponent, you should think about rewriting in log form. It'll get rid of the exponent. Exponent. X equals log base 3 of the square root of 8. Those two numbers look the same? I mean, those look like different formulas, right? If these are both correct, they better be the same because the graph looked like there was only one point where they crossed. Let's do a quick check. So on the one hand, let's compute log base 3 of 8 over 2. So that'll be log of 8 divided by log of 3, then divide by log of 2. I don't want to solve it. Solving isn't God damn it, Google. There. The number that you just told me. All right, let's see. Let's also compute the other thing. Let's compute the log of the square root of 8 divided by the log of 3. See if that gives us the same value. Does it? Nice. So there's actually a thing, an algebraic property that's appearing here. Yeah.
So what's the left side? That's entire log base 3 of 8. That's actually parentheses divided by 2.
Yeah. So take log, put 8 in it, then divide by 2. So if you want, you can throw an extra set of parentheses there. They're not necessary because you would evaluate the thing in the parentheses before the division. Yeah. Neato. So let's carry on, maybe in the interest of time. Well, no, I think thinking about order of operations is useful. Here's another equation to solve. Let's try to solve that equation. What seems like a good fast move? Let's convert to log. I see 3 to a power is equal to a number. All of the x's are in the power, so I think rewriting that in log form will make my life better. So if you rewrite that in log form, what do you get? Log base 3 of 8 equals x squared. Nice. What gets rid of that square? Square root. And let's worry about the plus or minus. X equals plus or minus log base 3 of 8. Feel okay? Oh, I lost the square root, didn't I? So let's think about this in a few ways. Maybe the first way I'll try to think about it is we have like graphical techniques. Let's try to graph this and see if the positive and negative things are both solutions. If we see two solutions and they look like symmetric over the x-axis, over the y-axis, then I think the plus or minus belongs. So let's pull up a graph. This time, this is going to be easier this way. Three to the x to the 2. Do I see two solutions that are symmetric over the y-axis? So I think whatever the solution should be, it should be plus or minus. Another way to think through this is the reason here why we could get rid of the negative is, well, 3 to the x itself could never be negative. But here the plus or minus just came from x. And the variable x is probably allowed to be negative. You could think about domain also to see that. People feel all right? Nice. So let's go back to this like vaguely applied question. So yesterday we modeled population of squiggles aboard the enterprise, and we got a population function model by P of t equals 2 to the t. Time is measured in hours since they found the first squiggle. Let's ask this question. The life support system will be overwhelmed once the population hits 3,000 twibbles. How long do they have to address this problem? How long will it be before the population hits 40,000? Yeah.
About 14 hours and 52 minutes. Or about 14.8727 hours.
Cool. How many people had already done the problem and got a similar answer? Cool. Let's talk through it. So let's try to model this problem in terms of some functions. So if we want to know when, when will the population hit 30,000. So what equation do we need to solve? Yeah.
That'd be 2 to the power of t equals 35.
Yeah. So there's a formula for P of t. We want to know when will it hit that number. So we need to solve that for t. Now that it's written down, does that look super easy to solve for t? Let's put it in log form. What will be the base? Base is 2. The thing inside is 30,000. All right. And I guess that is about 14 hours. So I guess here's one of the points to make. So we saw that exponentials grow really, really quickly. So if you want to know at what point will this exponential be pretty big, the amount of time it'll take to get there isn't that long. Exponentials grow really fast. Another thing that maybe this points out is if you take a logarithm and plug a really, really big number into it, I mean, the number will get bigger as you plug bigger numbers into the log, but it won't grow that fast. 14.9-ish isn't that big a number. Folks feel pretty good? Nice. And I guess you could convert to minutes and seconds if you wanted to, or decimals. Yeah. I don't think the problem specifies. I guess the SI thing to do would be, actually what would the SI thing to do be? I think it might just be to report the time in seconds.
14 hours, 52 minutes, and 22 seconds. So,
Yeah, but like just seconds.
um,
And then you would say it's approximately this many hours. I mean, I'm not going to do that right now. You would multiply by like 60 and then multiply by 60 again. So 4,600. So let's address some subtleties about logs. First, let's think about domains. And we'll see this a few ways. I think we'll address this question. We'll make an observation about domain, and then we'll read it off from a graph. So let's try to evaluate log base 2 of negative 30. And let's do this using a trick that we did a little bit last time. So that means if we want to compute log base 2 of negative 30, let's give it a name. Let's call it A for answer. Does that look like an equation that we could rewrite now in exponential form? I think so. The base would be 2. So this would mean we want to know when is 2 to the A equal to negative 3. So we want a power of 2, a power that we can raise 2 to, in order to give an output of negative 3. Is there any such power? No. Exponentials can never be negative. Exponentials stay positive. So this equation has no solutions. So in fact, log base 2 of negative 3 does not exist. That seem okay? In fact, that negative 3, we could be way more general than that negative 3. Would the same analysis happen if we had any negative number there? Yes. Would the same analysis happen if we had 0 there? Is any power of 2 ever equal to 0? No. You would just be like dividing by a bigger and bigger number. It gets close to 0, but it never makes it. So in fact, this thing in the parentheses must be positive. And let's put that into the language of domains. So apparently, what things when we plug into a logarithmic function, we can only plug positive things into a log function. So what's the domain of a logarithm? 0 to infinity. With a parentheses on both. On 0 because we want to exclude 0, and on infinity because we always exclude infinity. The domain of a logarithm is 0 to infinity. Notice that's different from square roots. Domain of square root is 0 to infinity inclusive, which square roots are different from logs, so that's not that surprising. Let's see this also from the visualization, from a graph. This is independent of base, so let's not include the base. So there's the graph of log base 10 of x. The domain is the set of x values you see on the graph. What x values do you see on this graph? Not x-intercept, that is the x-intercept. I see there are x values over all of this interval, starting just to the right of 0. There's a bar asymptote at 0, so 0 is not in the domain. So this agrees. Here's another thing that I think is worth checking. Let's try to use the same idea to evaluate log base 1 of 4. So let's use the same idea. So if log base 1 of 4 is equal to A for answer, then I need to find a number A so that 1 to the power A is equal to 4. Does that equation have any solutions? No, why not?
1 raised to any power is still just 1.
1 raised to any power is still just 1. So this has no solutions. 1 to the A is equal to 1 for all values that A might take. In fact, did the 4 matter? Does log base 1 make sense at all?
No.
No. And let's see why again by appealing to a graph. So remember, log of x is supposed to be the inverse to an exponential function. So I'll use base 10 just because this is base 10. No, I want to do base 1. So the log base 1 of x should be the inverse to 1 to the x. So let's graph x equals 1 raised to the y. Does that pass the vertical line test? So is that the graph of a function at all? No. Log base 1 isn't a thing. Whenever you want to talk about logarithms, what numbers can appear in the base? Well, I guess first of all, it can't be negative or 0. We won't allow those in the base of an exponent. We also won't allow 1. What numbers can appear in the base of a logarithm? Well, b has to be bigger than 0, and b cannot be equal to 1. So if we draw a number line of that, I guess if there's 0 and there's 1, here are the valid choices of b. Oh, that thing didn't actually show up that way. But now it did. Neat. So what is that in interval notation? Just to remember that.
0, 1,
Nice. Cool. Folks feel pretty good? So I think the closing thing I want to say in this particular packet is just a little bit about graphs. So we just described the domain of B being 0 to infinity. And let's go right to the computer-generated graph that we have up there. That we had up there. What would you say the range of this function is? Let's see this. Right. So you read off the range by seeing what y values are in there. Are these y values in the range? Negative infinity on the bottom up to? I guess on this graph I can't see any more than that. I'm going to make an argument that it's bigger than that, though. Let's change the x values. There are no negatives in there, so let's start at 0. Nope. Hold on. Start the x values at 0, and let's go on for a while. Does it look like y values close to 10 are still in the range? Oh, let's just add another 0. I may have zoomed out too much. So it looks like y values up to 20 are still in the range? Do you think I could do the same trick to see y values of up to 30 still being in the range? So what do you think the range of this is? Everything. Negative infinity to infinity. It'll just take a while before it gets to anything big. Right? Yep. So it'll take a while to get to 20, but it'll get there. The range of logarithms are negative infinity to infinity. Let's talk about something that we won't need to zoom out for. So you already told me this. Where's the x-intercept of logarithms? At x equals positive 1. Or 1, 0 if you want to give the point. Where are the vertical asymptotes of logarithms? Yeah. At x equals 0. And you know what? Let's also do a quick comparison. Let's look at the graphs of logs for various choices of b. What are the valid choices of base you might have in a logarithm? Not quite.
Anything but 1.
Anything bigger than 0 other than 1.
Then 1.
So let's try to graph such things. So does decimal have multiple bases? It does. Okay. So let's vary the trace of base. So let's take this base. Let's let it run from, I don't know, 0 to like 5. So there will be a problem when b is equal to 0 and b is equal to 1, but that's okay. Let's graph the log base b of x and see what it looks like. So there's the graph of log base 2. As the base grows, it flattens out, which I guess makes sense. It takes longer for that to grow because the bigger base exponent will grow. And I missed the bit where it became less than 1. So let's see what happens there. How do these graphs compare with graphs where the base is bigger than 1? Yeah, they look kind of like they're flipped over the x-axis. I think that agrees because exponentials did a similar thing, except flipped over the y-axis. But these are inboxes, so that seems sensible. Cool. So let's close this section with just some domain computations of some examples, because these are things that I like to ask about in homeworks. All right, so log base 2 of 3x minus 4. Let's try to compute. I guess this just wants the domain and the x-intercept. Let's try to find both. Let's try to find the domain. Let's try to find the x-intercept. What should we do first? X-intercept seems easy. Let's find the x-intercept. How do you find the x-intercept of any function? Yeah. Plug it in y equals 0 and see what happens. So let's set this thing equal to 0, and then we need to like solve for x. So to find the x-intercept, we need to solve log base 2 of 3x minus 4 equals 0. Oh, cool. That's now an equation in logarithmic form. All of the variables are in the parentheses. Does that look like our life will become better if we put it in exponential form? I think so. Let's put it in exponential form. What's the base? 2. 2 to the power 0 equals, and then it's the thing in the parentheses, 3x minus 4. And what is 2 to the 0? Yeah, anything to the 0 is 1. That look easy to solve for x? Yeah, what do you get? 5 thoughts. Are you sure about that? Yeah, I agree. I was making a sign error in my head. I was going to say negative 5 thoughts. People agree? Let's also think about domain. Alright, so the way to think about domain is think about what could go wrong. And let's go inside out and just think about what could go wrong in each ingredient. So if you only saw 3x minus 4, can anything go wrong? If you didn't see the log? No, that's fine. What about the log? Are there things that you're not allowed to plug into a log? Negative numbers and 0 are both bad. So if you want the domain of this, the thing inside the log needs to be strictly positive. That look easy to solve for x? Yeah, in fact, I think it's all strictly linear, so you could even like solve this directly without playing the game where you solve for equality and then check sampling points. Let's add 4 to both sides, divide by 3. What do you get? Yeah. And in fact, I think you wind up x greater than 4 velocity. Right, so depending on the velocity you take. Yeah, so one velocity is figure out when it's equal to 0 and then decide whether you want to the right or left. Since this is a very simple inequality, you can bypass that and just do it direct. That feel pretty good? Let's pick now one example from this list, and let's at least do the domain. So let's pick one of these three and compute its domain, and maybe x-intercept if there's demand. And think about this and think about which one you'd like to see. First one? Second one? Third one. All right, I think there was more demand for second than third, so let's do at least second and then we'll decide. So if we just want the domain of this, let's think about what could possibly go wrong. I see a fraction inside of the log. So what could go wrong with just a fraction?
If the bottom equals 0, it doesn't make sense.
The bottom equals 0, it doesn't make sense. When is that bottom equal to 0?
When x equals 1.
X equals 1 is bad. That sentence is a little bit vague, but I think it captures the meaning. I also see a log. What things am I allowed to plug into a log? Yeah. Okay, you answered the opposite of what I asked. Those are the bad things. Those are the things I'm not allowed to. You had the right spirit. So if you want to know what things you can plug in, you need to solve an inequality, which is the opposite of the inequality you just wrote. So let's see, because domain of any log, but natural log in particular, is 0 to infinity, 1 plus x over 1 minus x needs to be bigger than 0. This is now a slightly difficult inequality to solve. It's like there's some minimal amount of complexity to it. So what strategy should we use to solve this inequality? Multiply the denominator over to the other side. Here's the thing that could go wrong. So you want to multiply both sides by the bottom of a fraction to clear a denominator. If 1 minus x is negative, that would flip the inequality. So I'm going to suggest, in order to avoid that possible error entirely, let's solve equality, find the Vonnegut asymptotes, and then check some sample points. That's like the plan of attack we've had in the past. In fact, have we already found the Vonnegut asymptote? What's the Vonnegut asymptote? When is the bottom equal to 0? 1. So that'll be like one of the endpoints of the domain. 1 plus x over 1 minus x equals 0 at, if we just set it equal to 0 on the nose, does that look easy to solve too? Yeah. When is that equal to 0? Negative 1. Yeah, I believe that. Should those endpoints be included or excluded from the domain? Excluded. One of them, because it's a Vonnegut asymptote, you should always exclude those. The other one would result in the thing in the log being 0. Both have to be excluded. So let's check some sample points. What's a number to the left of negative 1? Negative 2. And let's see if we can do this just straight in our head. Plug negative 2 into that. Negative 2 plus 1 is positive or negative? Negative. How about the denominator? Positive. So, will the result be positive or negative? So, you check x equals negative 2. You find out that negative infinity to negative 1 should be excluded. What's a number between negative 1 and 1 we can check? We plug in x equals 0. What do we get? Positive 1. So is that something that makes us happy or unhappy? It works. So a 1 is allowed to appear inside of a logarithm. It's not in the base. It's allowed to appear inside of the logarithm. So negative 1 to 1 should be included. What's a number bigger than 1 we could check? Also 2. Will we get something positive or negative? I think it'll be negative. So it looks like the domain of this is just negative 1 to 1. Was that a reasonably effective review of how to solve inequalities involving complicated things? Ruby. So let's do one last thing. Let's think about graphs a little bit. I think at the end of today, I'm going to go to my office and adjust the schedule in Canvas and on this because I'll be a day behind where I thought I should be, which is okay. The schedule is very much aspirational. So let's try to sketch the graph of ln of 2x plus 1 minus 1, and let's graph by transformations. And let's start by just remembering these 3 facts. X-intercept is always at x equals 1 if this is y equals log x. Natural log of e is equal to 1. And there is a vertical asymptote at x equal to 0. Let's try to graph this function by transformation. So let's do it one thing at a time. What will that minus 1 do to the graph? Drop it down by 1. Will that move the vertical asymptote? I mean, I guess the answer to that question is yes or no, depending on what you mean by move. It's a vertical line, you move it down 1. It's the same vertical line. It's just moved down by 1. Where will this point go? 1, negative 1. Where will this point go? So there's the graph of ln of x minus 1. What will the plus 1 do to the graph? So let's do that. Let's track where each of those points and the vertical line will go. So where will the vertical asymptote go when we do that? Negative 1. Vertical asymptote at x equals negative 1. This point at 1 comma negative 1, where will it go? 0, negative 1. Where will this point at e comma 0 go? I guess whatever e minus 1 is, right? Yeah. Which is like, if e is 2.7-ish, it'll be 1.7-ish. But e minus 1 is fine. Yeah. So there's the graph of ln of x plus 1 minus 1. Now let's deal with that too. What will this 2 next to the x do to the graph? Not quite. Yeah, so it'll do something to the x values. It will divide them by 2, so everything will compress. So let's just see what that does. The vertical asymptote will now be at I think negative a half, right? It's at negative 1 now. All the x values will get divided by 2. Divide x values by 2. So there will be a vertical asymptote at x equals negative 1. This point at 0 comma negative 1, where will it go? What's 0 divided by 2? 0. Does the y value change when you do this? No. Nope. Where will this point, e minus 1 comma 0, go? I guess whatever e minus 1 over 2 is, right? Which we could get a decimal approximation, but I think I won't. E minus 1 over 2, comma 0. And then it should look like a logarithmic graph on the line. Does that feel pretty okay? Cool. How many people had already done things like look at the web walk for the thing that was, I guess, really assigned for last time? Hopefully those problems seem more reasonable now that we've actually covered the relevant content. Hope so. So with basically no time, maybe I'll give now a preview into what will happen next. So there are some rules that logarithmic functions follow called the logarithm laws. If I say logarithm laws, how many people have already heard that string of laws or something? Neither. So what we'll do next time is we'll mention the logarithmic laws. We'll say how to use them, and then we'll say something about where they fit. Nice. So, let's see. As a reminder, it's written on the board. On Fridays, since it's the Friday before spring break, I'll still be around at 1 o'clock, but maybe officially I'll move my office hour to 8 a.m. because I anticipate more people will be willing to come to an 8 a.m. office hour than a 1 p.m. office hour on Friday. I just headed back exams, go through and make sure I didn't screw up your exam. If I did, then let me know, and we'll get it fixed. And I think that's it. Cool. See you all tomorrow. Or later today, because I have my normal office hours today. I don't remember when last week, right? And then I should have seen it, but I don't remember. Oh, okay, cool. Yeah, it's possible that during those 3 days there might be one of these quizzes I like to give, but I'll have to make it up. I guess we get back on the Monday after. What's going away for?
Julie.
Oh, yeah. Cool.
Thank you.
Yeah. Cool. Send me something conforming to register.
Okay.
It doesn't have to be like the most official thing, but something that makes it clear that it's less used.
Okay.
Maybe I'll give a quiz that Friday. Maybe I don't have to decide it. If I do, then it's a good thing. Yeah, thank you. Ooh, let's stop the recording.